All right, intermolecular forces enrichment. So if you are watching this as an online student, you can download this file from the course website and try it on your own, and then this is the answer key. Or maybe you don't even want to download the file, maybe you just want to watch this video, hit pause, try it on your own, and then when you're ready to see the answers, you can hit resume. So these are the problems we did during class. Here's the first part. I gave you some molecules, and I asked you to identify the types of intermolecular forces. All right, so hit pause, give it a try on your own, and then when you're ready to see the answers, you can push resume. Here's the next set. I said for each pair, pick the one with the lowest boiling point, and then if there are 3 substances, like in number 2, rank them in order of decreasing boiling point, and then give a justification for your answer. So again, if you're watching this online, hit pause, give it a try on your own. When you're ready to see the answers, you can resume, or you can go directly to the course website and download the PDF and try it that way. So that's the second section. Third section, I ask you, which substance would you expect to have the highest boiling point and why? So of these 4 molecules, choose the one you think is going to have the highest boiling point, and then give me a justification for why you picked that. All right, and then the last couple questions are short answer. So what kind of molecules would you expect to have London forces, dipole-dipole, hydrogen bonding? Answer that, give it to your best effort as if this were a test, and then you can grade yourself. And then the last 2 are drawings. Draw a molecule of your choosing with London forces only. Remember that carbon must have 4 bonds. Draw a molecule of your choosing with all 3 IMFs. Remember that carbon must have 4 bonds. So if you're watching this online, hit pause, give these problems a try, and then resume the video when you're ready to see the answers. Or you can go directly to the course website, download the file, try it all at once, and then grade your work. All right, so first one, let's look at this. What kind of molecule is it? It's composed only of carbon and hydrogen, right? So that means it's got the name hydrocarbon. And we discussed on Monday, carbon and hydrogen have the same electronegativity, right? So that's nonpolar. That means that electrons are being shared evenly. So every substance has which IMF? London forces, right? So you just need to decide, you can call it London forces, you can call it London dispersion forces if you prefer. Just depends on which book you're looking at. And some books just call it dispersion, so don't be surprised if you see those used interchangeably. So now you just need to ask yourself, is there anything in addition to London forces in this molecule? It's hydrocarbon that's nonpolar. So are there any IMFs in addition to this? The answer is no, right? So this is London forces only, nothing else. Everything's going to have London forces. You just then need to decide, is there anything in addition to it? Okay, so for number 2, we can go ahead and write London forces because that's present in everything. And then, is there anything in addition to London forces? Hydrogen bonding, yep. And is it the entire molecule or just a specific portion? Just the OH, good. That's coming from this piece right here. Anything else? Good, dipole-dipole. Dipole-dipole is coming from where? The carbonyl, right? This piece right here. So this one has all 3. All 3 of the ones that we're covering in elementary organic at least. There are other intermolecular forces that exist, but we're only covering these 3 in our class. All right, so next one. Obviously have London forces because London forces are present in everything. And again, you could call it dispersion forces or London dispersion forces, right? Just be able to identify it either direction. Some books call it dispersion, some books call it London, some call it London dispersion, okay? Anything in addition to London forces? Hydrogen bonding, right? Coming from, again, the OH group. We'll learn how to name all of these molecules very, very soon. Okay, argon, monatomic element. Everything's got London forces, even if it's just a single atom. Is there anything beyond London forces here? No. So it's just London forces only. And then the last molecule, everything has London forces, so we can put that. That's our default answer. And then we just need to decide, is there anything in addition to London forces? The answer is yes. What is it? Dipole, dipole. Good. Coming again, just like up here, from the carbonyl. It's not the whole molecule that's capable of dipole-dipole, it's just the carbonyl. All right. Let's move on to the second section. Looking at some boiling points, deciding who's going to have the higher or the lower boiling point based on the structure. For each pair, choose the molecule with the lowest boiling point. If 3 are given, rank them order of decreasing boiling point and give a justification. Okay, so CH4, if you want to sketch that molecule, looks like this, right? That's its Lewis structure. And then here's the Lewis structure for methanol. There's a very, very, very big difference in boiling points here. Much, much, much big difference. It's not something you would miss. Let's go through and identify the IMFs, and then we can pick our answer based on that. We both have London, right? Both of these have London forces. Does methane, CH4, have anything beyond? No, because it's a hydrocarbon, no substitutions, right? So this is London only. What about this one? Right, plus hydrogen bonding. Hydrogen bonding is a pretty significant intermolecular force, right? This is a small molecule, this is a small molecule too, so they're of comparable sizes. So it's not like one of them is an 80 carbon chain and one of them's a little tiny molecule with hydrogen bonding. Because if this were an 80 carbon chain, the 80 carbon chain would be much, much higher, right? But these are comparable size. So the only difference here is one's capable of hydrogen bonding and one isn't. So who's going to have the highest boiling point?
Or, I mean, the monomer.
Right, this is going to have the highest boiling point. And the problem says to choose the molecule with the lower boiling point. So this one's going to have the lower boiling point. And then in terms of our justification, let's look at how we would need to describe this, the level of detail we should put on a test, right? So we would say these are comparable in size. Right, they're comparable in size. It's not like one's a mile long and one's itty-bitty short. The only difference is that one has H bonding and the other doesn't, right? H bonding is much stronger IMF than London only, right? Now, if you had drawn the Lewis structure and identified the IMFs underneath it, and then just kind of given me a couple blurbs off to the side, that would have been sufficient for me, okay? If you had sketched the molecule, the Lewis structure, and said, all right, this one's got London forces only, this one's got London and hydrogen bonding. Hydrogen bonding's way, way, way more significant intermolecular force than London forces, therefore, London forces is one's going to have the lower boiling point. Because think about when you boil something, right? Remember, boiling is called vaporization. Taking a liquid, particles in the liquid phase are close together. Now I wouldn't expect you to draw this on the test, right? Particles in a liquid, they're feeling all these IMFs towards each other. Right? We represent IMFs with dashed lines. To boil it, to vaporize it, you have to overcome your IMFs to boil, right? Which means the stronger the IMFs, the higher the boiling point, because that's more energy you've got to put in to overcome those IMFs. But just remember, do you break bonds when you boil? Do bonds break? No. Okay, if you write, this one's got more bonds to break, I'm going to have to mark you wrong, right? Because you're not breaking a bond when you boil something. You think about this as like a stronger magnet. It takes more energy to pull a strong magnet apart than it does to pull a weak magnet apart. So a magnet is more analogous to boiling, right? Because think about a magnet. When magnet sticks, we've got this one stuck on the board right here, right? When a magnet sticks to the board, that's not a chemical bond. That's an attraction. So IMFs are more comparable to magnets than they are to anything else. Because the stronger the magnet, the more effort you have to put forth to pull it off the board. If this were one of those super mega magnets, you know, I wouldn't be able to lift it off the board. But because this is a weak magnet, it sticks and comes off relatively easily. Does that make sense? Good. All right, let's look at number 2. Number 2 gives us 3 structures, and then because there are 3 structures, it asks, okay, since there are 3 structures, we need to rank them in order of boiling point, decreasing boiling point specifically. So all of these, this one's got London and H bonding, right? Coming from the OH. This one's also London and H bonding, again coming from the OH. And this one's London and H bonding, again coming from the OH. Let's look at chain length, right? Because that's the only difference here, right? They all have London forces, they all have hydrogen bonding. So the only difference here is chain length, right? This is a 2-carbon chain. This is a 3-carbon chain. This is a 4-carbon chain. So in terms of London forces, who's going to have the strongest London forces? Because they all have London forces, but the London forces are going to be significantly stronger in one of these and significantly weaker in another one of these. Which one's going to have the strongest IMFs total? The 4-carbon chain, right? This one's going to have the strongest IMFs. And obviously this one will be the weakest as a whole, right? If you add all these up, we're looking at the total, right? When you add them all up. And then this one's going to be in the middle. So if we're ranking these in order of decreasing boiling point, that means who goes first? Right, the highest first. If we're going in decreasing, that means highest first. So that means 1 butanol is greater than 1 propanol, which is greater than ethanol. And it's not a insignificant difference. Ethanol is about 78 degrees Celsius. Propanol's in the 90s. It's like 93, 94, 95. Call it 94. And butanol, it's like 117, 118. Right? If you had all 3 of these as liquids, you could distill this relatively easily. Right? We'll talk about distillation in the lab. But these are, you could easily separate that, right? If you have all 3 of them in a flask and you slowly lower the temperature, slowly increase the temperature, the ethanol will boil off first, and then the propanol will boil off second, and then the butanol will be the one we'll have left, right? Again, what's the difference? All have London plus hydrogen bonding. So what's the point of difference? The difference is chain length. All right, as you increase chain, you increase London. Good on this one? All right. Let's go on to the next problem. Which substance would you expect to have the highest boiling point and why? This is asking for the highest boiling point. So that means that we're picking the one with the strongest IMFs. So let's just go through and identify. We got all, they're going to have something similar. Right? I think we can figure it out. Right? Those are the key IMFs. Yes? Because all of them have London. Right? This has London plus one source of H bonding. This one has London plus how many sources of H bonding? 3. Water actually counts as 2, right? Because that's how that one would work. This is London plus 2 H bonding. And this is London plus dipole-dipole, right? Because that's a carbonyl. So when we're asking which one's going to have the highest boiling point, we're picking the one with the strongest intermolecular forces. Which one would it be?
The one with 3.
Right, glycerol. That's what the name of that molecule is. Come back to play in the biochem section. We talk about glycerides. Glycerides are fatty acids that come from glycerol. Right? The largest boiling point comes from the strongest IMFs. So if this were a test, and you wrote the molecule with the strongest IMFs will have the highest boiling point, and then you just identified the IMFs in each one of these, that would have been sufficient for me. All right. Let's look at next one. What kind of molecules would you expect to have London forces only? These are molecules that are nonpolar, right? Nonpolar molecules. Any molecule is nonpolar. So example, a hydrocarbon with no modifications. Remember, we say hydrocarbon is any molecule that fits the description CXHY, right? It's just carbon and hydrogen. So any hydrocarbon that fits that description would be nonpolar, right? The CH3OH, that's a modification, right? But CH4, that's just a straight up hydrocarbon. What kinds of molecules would you expect to have dipole-dipole? This would be polar molecules. This would also be molecules with what? A carbonyl, right? So C double bond O. That's 2 dots on the side. Go. And what kinds of molecules would you expect to have hydrogen bonding? So this would be molecules with NH, OH, oops, or FH bonds. So let's do some examples, right? If we had right, that would have hydrogen bonding coming from this. Or if you had right, that still counts, right? If you substituted an OH, let's put 2 OHs there just for fun, right? All of those would be hydrogen bonding, yes? So as long as your answer says it contains an NH, an OH, or an FH, that fits the description for hydrogen bonding. We good on this one? All right. Now for the drawings, you just need to apply these rules and then make sure that your answer actually is something that exists, right? Because carbon must have 4 bonds. So a dipole-dipole What did you draw? What does your chain look like?
I see it in the middle.
Okay.
I made a double bond with an on. 2 H's.
That works. That works. That's the simplest carbonyl you can have. So that works, right? That's absolutely fine. You can make this chain as long as you want it, right? As long as it contained a carbonyl. You could have made it as part of a ring. That would work too. Right? As long as you've got a carbonyl and carbon's got 4 bonds in every scenario, I'm happy. That's the simplest answer. If that works, that's great. Okay, London forces only. So this has got to be a nonpolar molecule. So any CXHY will work. How many carbons do you have in your chain?
I have 1 carbon and 4 hydrogens.
Okay, so yep, that's the simplest option. Any hydrocarbon will work. You can make it a 1 carbon chain, a 90 carbon chain. You could have made it a ring, right? So instead of having your carbonyl here, CH2, you could have made this. Right, that would work. And then molecule of your choosing, I should probably scoot this up a little bit. Molecule of your choosing with all 3. So this is going to be a molecule that needs to have a carbonyl, right? It needs to have a carbonyl. And it needs to have NH, FH, or OH in it, right? Because everything's going to have London forces. So what did you draw?
I put a C in the middle.
Okay.
And had a double bond with an O.
Okay.
And OH and a CH.
That works. That works, that works, that works. Right? And if you wanted to substitute C double bond O, make that NH2 instead, that would still work. Hydrogen bonding is coming from this. Right? You can get creative so long as your answer has a carbonyl, either an amino group or a hydroxyl group. You don't see a whole lot of FHs in organic chem, which is why we just kind of tend to focus on those 2 instead. All right. Let me stop the recording. And you online students, if you have any questions about this, please feel free to email me.